Hello and welcome. A man walks into a bar with a slab of asphalt under his arm and says, "A drink, please, and one for the road." In this video, we're going to take a moment to review the integration tools we've learned so far, and then look at strategies to handle a few types of trickier integrals. Let's hit the road. The first thing you should always think about doing is simplifying the integrand. Simplify, simplify, simplify. For example, it's much harder to integrate this expression, x plus 1 times x minus 1 plus cotangent x tangent x times the quantity sine squared x plus cosine squared x, than it is to integrate this function, which is equivalent, x squared. So if you have an expression that can be simplified, especially one that has trig functions in it, you might think about using some trig identities to try to simplify it if you can, or cancel things off. Anything that you can do to try to simplify the integrand, you can try doing that, and hopefully what you end up with is simpler to integrate. Next, you might look to see if there's a substitution that you can make. If you see a function, especially that appears inside of other functions, whose derivative appears with the dx, or can be put with the dx, then probably a substitution will take your integral and make it simpler, turn it into a simpler integral. So that's a possible technique as well. Then you might think about integration by parts. And for integration by parts, there are a few different kinds of classes of integration by parts problems, at least some basic ones. So examples would be a polynomial times e to the x inside of your integral. In that case, you let u equal the polynomial, you let your dv be the e to the x dx, and then you can use tabular method to bring the polynomial all the way down to 0, and the e to the x's stay as e to the x. And if you have a different form like e to the 2x, well then you might have some coefficients, but the basic principle would be the same. Same thing with a polynomial times sine x or times cosine x. If you let u equal the polynomial and then the dv be the trig function, either sine x or cosine x dx, the same kind of result. You can use the tabular method to get the same kind of result. Again, remember that the tabular method is just another word for integration by parts, a streamlined version of integration by parts. So then another kind of integral that you might use integration by parts with is e to the x sine x or e to the x cosine x, or variants of those. That's the kind where if you use integration by parts twice, and you can put it in the tabular method kind of form, then you end up looping back around to the original integral that you started out with, the integral of e to the x sine x, for example, here. Then what you do is you bring both of those integrals to the same side of the equation that you're going to set up, and then you just have a coefficient that you divide over to the other side. So that's the strategy for the exponential times trig function type integrals. And then you have other ones like the integral of natural log of x. So this one, you let u equal the natural log of x, and then the dv is the dx. And when you take one step of integration by parts, the new integral that you get, the integral of v du, ends up being a lot simpler than the original one. This also is the case for the integral of inverse sine x or inverse cosine x. Now, some of the new techniques that we've just learned in Chapter 7 are, in addition to integration by parts, are the 7.2 techniques, which were trig integrals. So that's if you have sines, cosines, secants, tangents raised to powers multiplied together inside of an integral, then you can think about using those techniques from 7.2. If you see a rational function, so a polynomial over a polynomial, you can think about using the techniques from 7.4, the partial fraction decomposition technique. And if you see radicals like the square root of x squared plus a squared, or square root of a squared minus x squared, or square root of x squared minus a squared, if you see radicals like that, then you can start thinking about the 7.3 techniques. But again, for those, you want to also check if there is any simpler substitution before you jump into the trig substitution. If you can do a straightforward substitution, then that would be much easier a lot of the time. But if you can't, then you can go in and try it with trig substitution. I should also mention that this works when you don't just have a square root, but if you have a 3/2 power, it also works pretty well. It would mostly work with the root of 2, so like a square root. But if you have the inside raised to the 3rd power, if you see that 3/2 power, which still means like it's a square root, but it's just also raised to the 3rd power, then that would work as well. Or a 5th raised to the 5/2 power, or so on. So you might see some examples like that as well. And trig substitution would still work in those cases because it'll collapse the radical part of it down. And then if nothing works so far, you've done all these other things and you're starting to look like this guy over here pulling his hair out, then you can try substitution again, maybe a trickier substitution, and we'll see some examples of that in this section, 7.5. Maybe try to manipulate the integrand, like rationalize the denominator or use some trig identities. We'll see an example of that as well. Maybe try integration by parts again. You can try setting it up, switch the u and the dv, perhaps, and see if it works like that. Or after you take an integration by parts step, look at your new integral and see if it's doable, see if there's any other technique you could apply to it. So integration is more of an art form than a science, although it's a little bit of a mix of both. Let's see which technique we're going to use for example 1, which is the integral of dx over 1 minus cosine x. Now here, if we try to do a regular u substitution, let u equal 1 minus cosine x, for example, the problem is the du has a sine x, which we don't see with the dx. So a straightforward substitution is probably not going to help us out here. But maybe what we could do is try to manipulate the inside. We see this trig function right here. Maybe there's a way to manipulate the inside so that it's easier to integrate. In particular, when you see this 1 minus cosine x, does that remind you of any kind of identity? Maybe not exactly, but if we modify it a little bit, there's an identity that we could use to maybe try to simplify a little bit. So if you think about 1 minus cosine x, it's really close to 1 minus cosine squared x. In fact, if this were 1 minus cosine squared x, then the bottom would become sine squared x, and that would greatly simplify the radical. So how can we make this 1 minus cosine squared x? Well, we can multiply the top and the bottom of the fraction by 1 plus cosine x, by its conjugate, in other words. So let's write this out here. We have 1 over 1 minus cosine x. That would be a huge negative sign, minus sign there, that fraction bar. Okay, so we have 1 over 1 minus cosine x. If we multiply top and the bottom of that fraction by 1 plus cosine x, then the bottom becomes 1 minus cosine squared x. Let's not forget our dx. So we have 1 plus cosine x on the top. On the bottom we have 1 minus cosine squared x. And now we can rewrite 1 minus cosine squared x as sine squared x. And this is great because the whole issue about the original fraction, and when we think back to it, is that we had two terms on the bottom of the original fraction, and you can't just break it up into 1 over 1 minus 1 over cosine x. The fractions don't really work that way. That only works when the minus is on the top of the fraction. But when the minus is on the bottom of the fraction, then you're kind of stuck. So here we got unstuck by using this knowledge of the trig identity, 1 minus cosine squared equals sine squared. That helped us out with collapsing radicals, and it also helps us collapse the bottom of the fraction into a single term, which is great for trying to simplify. Okay, so now we can break this up. We can break this up into 1 over sine squared, and then plus cosine squared over cosine over sine squared. And one of the reasons for maybe doing that is so that we can split the integral into two smaller integrals. Now, if we think about the cosine x over sine squared x, let's take that to the side. What we can do is we can either just tackle that directly as an integral by using a substitution, But you can also break this up into other trig functions. So this is the same thing as cosine x over sine x times 1 over sine x, which is cotangent x cosecant x. And that actually makes it a little easier to integrate, because we can integrate integrals that have cotangents and cosecants all multiplied together. That was the 7.2 strategies and techniques, trig integrals. So we have 1 over sine squared x, which is the same thing as cosecant squared x, which we can integrate. And then we have plus cotangent x cosecant x dx. Now those two are straightforward integrals. If we separate this out into the integral of cosecant squared x, well, that's going to be negative cotangent x. And then if we have the integral of cotangent x cosecant x, that's negative cosecant x plus c. Great, so with a little bit of manipulation of the inside of the integrand, we were able to write it in such a way that we could eventually just integrate it in a straightforward way. When it came to the integration, it was actually pretty straightforward. The integral of cosecant squared is negative cotangent, and then the integral of cotangent cosecant is negative cosecant. Now once again, if you didn't see how to take this cosine x over sine squared x and break it down into cotangents and cosecants, that's okay. You can do, if you want to integrate that, you can let u equal sine x, and then the du is sitting up right on top. It's cosine x. So you can do a substitution for that part of it as well. This just turns out to be slightly more straightforward and faster to get there. So there are multiple ways of doing these integrals. Okay, so that's it for example 1. In the next part, we'll take a look at example 2. Thanks for watching. See you next time.